I'm Anil Kumar, and on request of my students, here is a detailed explanation of sketching graphs. Now we'll follow the algorithm to sketch the graph. We will sketch graph of a polynomial function 3 times x to the power of 5 minus 5x cubed in this video. So while sketching, we'll look into domain and range, symmetry. I've written domain here again. It should be, let us say, we'll make it end behavior. Okay, X intercept, Y intercept, asymptotes, first derivative, and from first derivative, we can find increasing, decreasing intervals, and thereby find local maximum and local minimum. Then we will analyze the second derivative to find concavity and point of inflection. So let's do them one by one. Since we have a polynomial function, it means the domain is all real numbers. So we can write here domain as all real numbers, right? How about range? Now degree is odd, that means range is also all real numbers, right? So range is also y belongs to real numbers. Let me write like that, okay. Now the end behavior, let's go to end behavior. Since the leading coefficient is positive, right side is up, right? So right side is up. And since the degree is odd, we are looking for opposite ends, right? So that is how it is. So end behavior is that when x approaches negative infinity, y approaches negative infinity, and when x approaches positive infinity, y approaches positive infinity, right? So from the equation directly, we can get all this information. And now let's look into symmetry of the function, right? To find symmetry of the function, we will do some calculations. We are given the function f of x as equal to 3x to the power of 5 minus 5x cubed. So let us find what is f of minus x. So substitute x as minus x. We get 5 minus x cubed. And now minus x to the power of 5 will be minus. So we get 3x to the power of 5. And this sign will also become minus. So it becomes plus here. So plus 5x cubed. Now you can factor out minus. Then you get what? We get 3x to the power of 5 minus 5x cubed, right? That indeed is minus of f of x. Since f of minus x, I should have written this minus inside, okay, f of minus x is minus of fx, we say that the function is odd function, right? So we know this is odd function. Odd function is symmetric about? Symmetric about what? It is symmetric about origin, right? It's a point symmetry and symmetric about origin. So that is the information about symmetry. Let us fill it in here. So we found that this has odd symmetry. Okay. Let's continue to find x intercepts and y intercept. Now to find x intercept, what should we do? We have to get f of x as 0, right? So let us see how to find x intercept now. So f intercept means f of x equals to 0. That is to say, f of x is 3x to the power of 5 minus 5x cubed. Let's factor this. So we could factor, okay, x to the power of 3. We get 3x squared minus 5. Now if that is 0, then x is equals to 0. That is one solution. The other we can get by equating 3x squared minus 5 to 0, right? And that gives us two solutions. One is x is equals to 5 over 3 square root plus, and the other one minus, right? So we have 3 x-intercepts. So we have x-intercepts at x equals to 0, square root of 5 over 3, and square root of minus of 5 over 3, right? So these are the 3 x-intercepts for us. Let us also find the y-intercept here, right? So y-intercept is when x equals to 0, what is the value, right? Okay, so that is to say, what is f of 0 equals to? So if I substitute 0 in this equation, I get 3 times 0 minus 5 times 0, that is 0. That means 0, 0, or origin, right, is indeed the y-intercept, right? Intercept, right? Intercept. Okay, so let's fill in this information also. So we'll write x-intercept is at x equals to 0 and at plus minus square root of 5 over 3. As far as the y-intercept is concerned, it is at origin, so let me write 0, 0 here. Okay. Now, since this is a polynomial, we do not have any asymptotes, and therefore we will not analyze anything about asymptotes. Now, let us find the derivatives and figure out the maximum and minimum, the local maximum and minimum for the given function, right? It will not have x, because it is going from one infinity to the other, so there won't be any absolute maximum minimum, right? So the function given to us is f of x equals to 3x to the power of 5 minus 5x cubed. First derivative of this function is 15x to the power of 4 minus 15x squared. So we can take 15x squared common. So we get x squared minus 1. Now for critical number, f prime x, or the first derivative, should be 0. Now that will be 0 at x equals to 0, right? So we have one critical number at 0. The other one is at plus minus 1. So we have 3 critical numbers in this particular situation. Now, let us analyze these critical numbers. To analyze these critical numbers, what we can do is take test points, right? So we'll take test points to analyze the critical numbers. So let us say that that is the line on which we can take the points which are 0, minus 1 and plus 1, and we are trying to analyze the first derivative. Correct. Equation for first derivative is right there. 15x squared minus 1. Now we can take a test point as like beyond minus 1, between infinity as minus 2. Here we can take minus half, plus half, and 2. So these are the critical points or test points which we can take in the interval from minus infinity to minus 1, and minus 1 to 0, 0 to 1, and 1 to infinity. Now, if I substitute minus 2 here, we know the first term is always positive since it is x squared. Now that 2 minus 2 square will be 4. 4 minus 1 is positive. So in this interval, we expect positive derivative. Now positive means that the function will be increasing, right? So the function will be increasing from minus infinity to minus 1, correct? So that is how it will behave. Now in the interval from minus 1 to 0, if I substitute minus half, first term is positive, the second term will be negative, right? So it will be negative, and that means the function will be decreasing, right? So this is about the function f of x, correct? If you substitute half, then the second term will be negative, first being positive. So it will be again decreasing in this interval, and on 2 it will be increasing since both will be positive. And from here, we clearly get our maximum value, which is local maximum. And here we have a local minimum. So you can see that the local maximum is at -1. So we can find the value of the function at -1. So let's substitute -1 in the given equation. So if I substitute, I get 3 to the power of -1 to the power of 5 minus 5 times -1 cube, and that gives you, this is negative, right? So -3, because this is -1, and this is also negative, so it will give us negative, and negative becomes positive, +5, and we get a value of 2. So f of -1 is 2. That is our local maximum, and also find local minimum, which will be at 1. So if I substitute 1 here, I get 3 -5. Let me write like this, and that is -2. So we get local maximum and local minimum. Maximum being at -1, 2, and the minimum at 1, -2, right? So let's make a record of this. So what we found here was that the local maximum, so let me write here, local maximum is at -1, and the value is 2. And the local minimum will be at 1, the value is -2, right? These, whatever values you're getting, they're working out well with the odd symmetry also, right? So you can check your values with odd symmetry. We found that X intercepts are symmetric about origin. Maximum minimum values are also symmetric about origin, right? Interval of increasing and decreasing, what we really got for f of x, first derivative, right? So when we analyzed, we found that critical numbers for us were at 0, -1, and +1, and the intervals from -infinity to -1, it was increasing, then decreasing, decreasing here, increasing there, correct? That is how it was. So that is how it is. Now, so we know all this. Let's go for the second derivative. So we found that the first derivative in this particular case was, we took 15x to the power of 2 common, x squared, and inside second term was x squared -1, correct? Now starting from here, we could actually do the second derivative. Do it right here. We found that the first derivative of this function is 5 times 3, 15, x to the power of 4 minus 5 times 3, 15, x squared. The second derivative is going to be 15 times 4, which is 60x cubed, minus 15 times 2, which is 30x. So you can take 30x commons. We have 30x common. We are left with 2x squared minus 1, right? So that gives us the second derivative. Clearly, we can see that there are 3 critical points here to analyze. So now we have the second derivative with 3 zeros. First one, let us say this one, is at 0 itself, right? The other two are at, when you equate 2x squared minus 1 to 0, you get value of, this is 0, and this one will be at x equals to 1 over square root of 2 with positive and negative sign, correct? Now, what is 1 over square root 2? Let us test it out. 1 divided by square root of 2 is equal to, in decimals, 0.7 approximately, right? So we will say this point is minus, well, let's write 1 over square root 2, and the point here is plus 1 over square root 2. Since it is 0.7, we could take half and minus half as our test point in this interval, and we could take 1 and minus 1 in the outside interval. Now let us try to find the concavity in these intervals. So in the interval from minus infinity to minus 1 over square root 2, if I substitute minus 1 in the given equation, then what do I get? Minus 1 will make the first term 30x as negative. So we have negative times the second term. If I write minus 1 here, square is going to be positive. So this is 2 times 1. So that is positive, right? Negative times positive, when you multiply, you will get negative. So we get negative in this interval. Negative means that the concavity will be concave down. So the graph will be kind of like this. Correct. If I substitute minus half here, first term will be negative, the second term will be positive, and their combination, if I substitute minus half here, in that case, second term will also be negative, right? Minus half. So that is 1 over 4, it will be negative. And combination of two negatives when multiplied will give us positive. Positive means concavity will be concave up, right? Now if I substitute half positive, the first term is positive, the second term will be negative, right? Second term will be negative, and product of these will give me negative, correct? Negative will mean concave down, right? If I substitute 1, which is positive, for the first one, this is also positive. Two positives when multiplied will result into a positive. That means concave up, right? So that is how the concavity is going to change. From here clearly we see that we have a couple of point of inflections. The concavity changes at each one of these points. So all these three critical points result into point of inflection, right? So we have 3 point of inflection, one at 0, the other two at plus minus 1 over square root 2, correct? So these are the points of inflection for us. So what we can do at this time is calculate the value of the function at 1 over square root 2, right? So let us find the value of the function at minus 1 over square root 2 and also at 1 over square root 2, right? Let us evaluate the value of the function at f of 1 over square root 2, which is 0.707. So we get 3 times 0.707 to the power of 5 minus 5 times 0.707 to the power of 3 equals to. So we get this value is minus 1.2, let us say 4. Okay. Now if I calculate the same value here, which is minus, let us do this also. So we get 3 times within brackets minus 0.707 to the power of 5 minus 5 times within brackets minus 0.707 to the power of, that is q, is equal to, we get value as let's write this as 1.24. So it works out fine with the odd symmetry also. It's kind of a test for you, right? Now we have points of inflections, we have maximum, minimum, local, and intercepts. We know domain and range, and we know the general behavior. So it's time to sketch the graph knowing all this information. So let's begin by making a proper scale. So what we really see here is that the maximum and minimum value is minus 1, 2. So basically we can have scale, we can use 4 units, 1, 2, 3, 4 units for 1, right? 1, 2, 3, 4 units for 1. So this is minus 1, and then 3, 4, this is 2 for us, and 1, 2, 3, 4, minus 2. Similarly here, 1, 2, that becomes 1, and then 1, 2, 3, 4 becomes 2 for us. So 1, 2, 3, 4 minus 1, 1, 2, 3, 4 minus 2. So let's plot the maximum and minimum value. Maximum is at minus 1, 2. So minus 1, 2. So that is a turning point, right? Maximum is a turning point. Minimum is 1 minus 2. At 1 we have minus 2. That is another turning point for us. Now the graph is going in this portion in that direction, and here we have X intercept on the left side of this graph, which is at minus square root 5 over 3, right? So let's find what is 5 over 3 square root. So within square root, 5 divided by 3 is equal to, in decimals, 1.29. So it is approximately 1.3, right? This is plus minus 1.3, let us say, right? So that is the X intercept. So 1.3, since we have 1, 2, 3, 4.25 here, so around this point. So what we can do is you can bring the graph down in this fashion here, right? So that is concave down. It matches with this part also. Do you see that? From minus 1, we have concave down. So that is how it is. Now that's a turning point, right? Now as we move, we come across the point of inflection, which is at 1 over square root 2 minus, right? And the point is at 1.24, right? So it is 0.2, 0.4. 1.24 will be slight 1.24, and the value is 1 over square root 2, which is 0.7. So 0.7, this is 0.8 for us. So somewhere here 1.24. So we have a point of inflection kind of here. Now since it is a point of inflection, the concavity will change. So during this time we have a concave down graph, right? But from here we'll change it to concave up as shown here. That is very important to understand, right? Now the second point of inflection is at 0, right? So at 0, the value of the function is 0. That is also our y-intercept. So our concavity from here will be concave up. So I'm purposely making it like this so that you appreciate the change in concavity. You get the idea, right? Then we have a point of inflection at 1 over square root 2. And the value is minus 1.24, which is symmetric to this point. Do you see that? So that is how you could get symmetric point at point of inflection, which is kind of here, right? So at 1 over square root 2, which is 0.7, so 0.8 is here, so somewhere here, correct. So up to here, the graph is concave down. Do you see that? Concave down. So we'll make concave down here, kind of like this. And then we have a minimum, which is concave up. So we'll connect it with concave up, this minimum, and then extend, going through the X intercept, which is at 1.3, right? So 1.25 and somewhere there, correct? So it will go now like 1.3, kind of like this. Do you see that? So that is how you should be sketching your graph. And now we can actually label it. So we can say that this point is local maximum, and local maximum for us is at minus 1, 2. At 1, 2, we have local minimum. We have 3 points of inflections, correct? So these are our points of inflections we have already given. These are our X intercepts, correct? And behavior is clear. I hope this method clearly demonstrates how we can use the algorithm to accurately sketch the graph of the function. So polynomial functions are continuous smooth curves. Our degree will be having domain and range of all real numbers, and clearly the end behavior, as x approaches minus infinity, y approaches minus infinity, x approaches positive infinity, y approaches positive infinity, since the leading coefficient is positive. So everything comes together when we make such a graph. I hope that really helps. I'm Anil Kumar. You can subscribe to my videos and learn a lot. Thank you and all the best.